So hello smarties again and welcome to my channel. So this is going to be a continuation, or I would say a continuation from what we talked about on my previous video where we looked at the Lewis structure of compounds. Now we're going to look at the problem. Technically this is problem 3, and we're going to look at how we're going to draw Lewis structures of different compounds. And it's quite really important because you need to know how to draw Lewis structures, because this is really important in organic chemistry, and majority of questions and also drawings and diagrams is all related to how to draw Lewis structures of compounds, and also compounds involved in various chemical reactions as well. So before talking too much, let's look at these particular examples here. We have 4 examples, 4 different structures, and we just have to imagine what these compounds look like. Hydronium ion is quite impressive because it comes from water, and water is kind of a neutral species. At some particular point it could undergo, okay, this pen is not working properly, I'll look for a better pen. Where is it? Over here? Yeah, found. Yeah, so comes from water, and water, once it accepts a proton, what it forms is an hydronium ion. So hydronium ion, the structure of hydronium ion is quite impressive because if you're going from water, water has oxygen attached to 2 hydrogen atoms, and from there we know that water, the oxygen has 2 lone pairs, and these 2 lone pairs, what happens then is that this hydrogen ion is charged and it doesn't have any electrons in its s orbital. So what happens then is that this lone pair gains a proton by sharing the bond to form an hydronium ion. The lone pair, and the overall charge is a positive charge on the oxygen. So in this case here, a typical example of this is this particular structure over here. So in here you see water, we have oxygen, and we have 2 hydrogens, which are the white balls over here, and these 2 naked bonds over here are actually referred to as lone pairs because there's no atoms attached to this particular functional group over here. So these lone pairs had 2 electrons, and if these 2 electrons then grabs this proton which has a positive charge, then you form an hydronium ion, where you have a lone pair, a positive charge on the oxygen, and you have 3 atoms of hydrogen bonded to the oxygen. So in this case here, why we have a positive charge is because the oxygen that was once neutral is losing an electron, or a lone pair of an electron. So if you are losing a lone pair of an electron, then you form a positive charged species. However, if you're a neutral species and you gain a lone pair, or you gain a bond, the pair, then you form a negative charged atom, which is oxygen in this particular case. But anyways, that's just something you need to note, or just to be careful about. In terms of that, we're going to focus more on formal charges in my future videos, but this is just a little stuff to just understand a little bit. So that's about it for hydronium. And next we have dimethylamine. So dimethylamine has a molecular formula of CH3 and HCH3. So this one is quite impressive because we can just draw straight off from this particular structure. So what do I mean by that? What I mean is that we have C, 3 hydrogens attached to the carbon with a dash, and over here we have nitrogen attached to a hydrogen atom, the bond, and then we have nitrogen attached to a carbon, and this carbon is attached to 3 hydrogens. So what is missing here is a lone pair on the nitrogen. And why do I say we are missing a lone pair? If we count the valence electrons we have for this overall species, you realize that once you distribute all the electrons in their respective bonding pairs, what you're left out is just 2 electrons. Now those 2 electrons then moves over to the most electronegative atom, which in this case is nitrogen. So a little homework for you is to do the calculations for the number of valence electrons, distribute them all into the respective bonding pairs, and then figure out whether you are going to gain 2 more electrons left or not. Anyways, that's about it for the structure, and an example of this is this molecular model kit over here. So in here we have our dimethylamine over here. So in here we have carbon, which is a methyl group. Never forget there are hydrogens on these carbon atoms here, and there are hydrogens on these carbon atoms here, and there are hydrogens on this carbon atom over here. But looking at this functional group over here, we have a nitrogen atom over here. This nitrogen atom is attached to a hydrogen, which is indicated by the white ball over here. However, we have a lone pair over here where there are 2 electrons, and these 2 electrons makes this nitrogen over here to be quite a much more electron giving, thereby being able to accept protons or compounds to form a charge on this particular nitrogen. But that will be focused more on future videos as we look at nitrogen reactions in organic chemistry. So next we have is propane 2-ol. So propane 2-ol has a molecular formula of CH3 CH into bracket OH and then CH3. So if I'm drawing the structure, I will draw it relative to how they are all written over here. Carbon attached to carbon, carbon attached to this oxygen. At the same time, this carbon is attached to this carbon. So what I have here is CH3 attached to this carbon, CH. However, we have a OH. Sorry, just got to make this a bond. Oxygen attached to a hydrogen, and the same carbon is attached to this particular carbon over here with 3 hydrogen atoms. So this is propane 2-ol. So don't forget to draw your lone pairs because that is critical in Lewis structures. So you put your lone pairs over here on the oxygen, and if you do the same calculation you did over here, you should be able to put the 2 lone pairs on the oxygen, which is the most electronegative element in this whole molecule. So an example of this structure is this diagram, or sorry, this model kit I have over here. In here you have a methyl group. You can see the bond is free rotation over here. We have another free rotation over here, another methyl group. We have a hydrogen over here on this carbon. However, this carbon is attached to this oxygen, and this oxygen is attached to the hydrogen over here. This hydrogen here is quite easily can be removed at some particular point. However, this oxygen here could actually accept protons as well using its lone pair present on this particular atom. So that's about it for propane 2-ol. And lastly, we have borane. So borane is from boron, but this boron is attached to 2 or 3 hydrogen atoms. So in this case here, 3 hydrogen atoms. What we have as a result of that is BH3. So this guy is in group 3 and it has 3 electrons. It shares electrons with the hydrogen atoms and it doesn't form any charge at all. And this is in period 2 as well. So as a result of that, we have this simple structure which we have over here. You have boron attached to 3 hydrogen atoms, and that's about it for all the structures over here we have overall. Anyways guys, thanks again for watching, and I hope you enjoyed it. I hope you saw reasons as to why these compounds are actually exhibiting these particular forms and structures in nature, and we're going to be using them mostly in some of our reactions in organic chemistry. Overall, thanks for watching. Please don't forget to hit the like button, share and subscribe with everyone around you. Have a good day guys. Peace. Love you all. Bye and be smart.